Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is a second video in a series on plane curves and parametric equations. We're going to start talking about how to graph parametric curves by hand. And there are actually 4 techniques for graphing parametric curves, but this is, for by hand, the easiest way to graph a parametric curve. Now, the second way is for really tough curves, and but still done by hand. The third way is by building a table of values, which you should never do, so it really is not a way to graph. And then the fourth way is using technology when things are just impossible to graph by hand, and we'll get into that in a future video. But let's go ahead and start by doing something called eliminating the parameter. So remember that a parametric equation, or a set of parametric equations if you prefer, is a curve described by x equals some function of time and y is equal to some other function of time. It's an Etch-a-Sketch. Okay, so one knob controls the x values and the other knob controls the y values. If you're given a set of parametric equations, you can eliminate the parameter by doing this process. The process of rewriting a parametric equation as a single equation in Cartesian form is called eliminating the parameter. So one thing to note here is that many, if not most, of parametric equations cannot be written or cannot have their parameters eliminated. It's very, very challenging to do that normally. However, out of a textbook, a lot of them can. They're more simple examples. Before we get started doing examples, let's just start a very good habit of mentioning any restrictions on the ranges of those parametric equations, because that's going to be critical. I will also probably mention domain restrictions if we have any. The reason for that is not going to be very apparent until we run into examples where that happens. So we'll just wait and hold off, and then we'll showcase why that's important. So here's our first example, and note that if you watched my previous video, these are the parametric equations from the previous video, where we built a table of values and found out that this was representative of a line in the Cartesian coordinate system. Eliminating the parameter here, first of all, I'm going to mention there are no domain or range restrictions on either of these. That is, this function right here is a line, x equals 2t. T can be anything we want, and x will be accordingly anything. It's just twice whatever t is. Same thing with y. T can be anything we want, and therefore y will just be that plus 6. So y will be also anything. So this is just a heads up. The domain and range are unrestricted here. And note how I do that. I just say that there's no restrictions on t, x, and y there, mainly because when you eliminate a parameter, you can lose sight of those restrictions. You eliminate a parameter here, we're going to find out that this is actually the equation of a line, but it turns out that sometimes that equation can be restricted in parametrics just because of some subtle restriction on t or on y or something like that that we're not aware of. Again, we'll run into that. So how do you eliminate a parameter? Well, you solve one of these equations for t and substitute that into the second equation. I generally would recommend solving this equation here involving x, solve that for t, and substitute that into the value of t for the second equation. There we go. I've written out kind of the process, at least for some parametric equations. You pick an equation where you can solve for t. The top choice would be the equation with x, if possible. Solve that equation for t, substitute into the other equation. So let's go ahead and take that value or that equation x equals 2t and solve for t. So you get x over 2 is equal to t. And then we're going to plug that in to the second equation. Y is equal to, instead of t plus 6, it's x over 2 plus 6. And you're done. That's it. That's your Cartesian form of your parametric equation. A lot of people would prefer to write this, I think, as 1/2 x plus 6. So let's see, that's a line with y-intercept at 6 and slope 1/2. And there we have it. That's the line that we get. We have our x and y axis there. The only thing that you don't get from the Cartesian form of this parametric equation is the path of travel. So it is kind of important to indicate the path of travel, not just kind of, it is important. So we're going to go ahead and just allow t to be 0. That would imply that x is going to be, if you look at your equations, which are up above, x would be 0 and y would be 6. Now, I do want to tell you that this is not the same thing as plotting points. So we're not plotting points to graph this. We're just trying to figure out what is the path of travel. When t is equal to 1, you see x is 2, y is 7, and that happens to be the 2 points that I plotted previously. So we can see the path of travel goes this way. Little heads up that every once in a while you get parametric curves that can rebound and come back the other direction. That's not going to be the case with this because as time increases, x will always increase. And as time increases, y will always increase. So that's another way that you can figure out the path of travel. Let's try a different example. Eliminate the parameter and sketch the parametric curve for the parametric equations x equals 1 over t, y equals t plus 1. Again, I'm going to just start by mentioning any domain or range restrictions that we see. The only thing I can see is that t cannot be 0. If time is negative, x is negative. If time is positive, x is positive. So x can be positive or negative, but it just will never be 0. In fact, I should mention that here. X will never be 0. That's kind of important to note because maybe when we eliminate a parameter, we find out that for some reason in our manipulation, we think that x could be 0. And it turns out that because time can't be 0, or at least x is 1 over time, that will never be a 0 value. Let's go ahead and eliminate a parameter. And again, I'm going to choose the equation involving x because, well, it's just much easier to work with, and in the long run is a better choice. Solving that equation for t, you get that t is equal to 1 over x. Substituting that into our y equals equation, you get that y is equal to 1 over x plus 1, which again, you could see that x can't be 0, so that takes care of that, right? So this is what we're going to go ahead and graph as our Cartesian curve for this parametric set of equations. And as you can see here, using our base graphing skills here, graphing skills and transformations, we see that our graph looks like this. That was kind of a weird mouthful to say there. Now, like I said earlier, the one thing we don't get from the Cartesian version of the curve by eliminating the parameter is the path of travel for the particle. So let's go ahead and take a gander at what the path of travel might be. We're going to split this into two possibilities. Either t is greater than 0 or t is less than 0. If t is greater than 0, think about a number that's slightly greater than 0, like 1, right? Well, if time is 1, x will be 1 and y will be 2. So I'm going to go ahead, I'll use red to start that. So when x is 1, y is 2, we'll just plot that there. And then let's increase time. When time is 2, we get x is 1/2, so it's closer to the y-axis, and the y value will be 3. So we will be right about here. So it looks like we're traveling in this direction, and that is actually true. Now you might say, wait a second, that means that we'd have to have time values that are positive, which start us way over here. And that is true. Try time values of something like, if you let t equal 1 over 1,000, it's a very small but positive time value. X will be the reciprocal of that. It'll be 1,000. So it'll be way over in this direction. And the y value will be 1/1000th plus 1, which is basically right above 1. So we do actually start way on the right edge of this graph, and it just starts carving out this way. So this is the path of travel that the particle moves. And when I say the particle, I really mean like if there was a particle represented by this parametric equation, the set of parametric equations, that's the path it would travel as time starts from 0 to infinity. Now let's worry about the negative time values. So think about a negative value for t, like t equals -1. If t is equal to -1, x will be -1 and y will be 0. So x would be -1, y would be 0. Well, the way I've graphed it is basically right there. And then as t gets larger, remember, we're trying to see the path it travels, so you want to let time be slightly bigger than or larger than -1. So you have to do like -1/2. That's to the right of -1. Very important to know that. As t goes to -1/2, so as time increases, the x value is the reciprocal of that, so it's -2, and the y value is -1/2 plus 1, or 1/2. So we're at -2, 1/2. So it looks like our path of travel is this way, which it is. So there you go. Let me go ahead and just showcase that path of travel again, right through here. It's probably, I think, for most people, the hardest part is the path of travel. If you don't believe me, then try a time value that's lower than -1. You try a time value of -10, for example. Remember, the x value is the reciprocal of that, so it's -1/10, and the y value is that time value plus 6. So -1/10, -4. -1/10, -4 would be like somewhere around here or further back, whatever it is, but it would be somewhere around here. So again, time equals -10, you're around here, and then time equals -1 is right there. So it's definitely, the particle is traveling in that direction. Really kind of a very cool way to graph a parametric curve. Now we've seen that eliminating the parameter often requires solving one parametric equation for t and substituting that into the second. However, this is not always the most straightforward approach. In fact, in this case, that would be a terrible approach. You might want to use some type of trig identities. And by the way, this is also why this topic generally sits within a trigonometry course, because you're using trig functions quite a bit when you're dealing with the parametric equations or parametric curves. There's my hint. When faced, there should be a D with that. When faced with parametric equations involving trig functions, look for identities, trig identities specifically. So I'd love to take x and substitute it into y somehow. Well, one way that you can rewrite y is using the trig identity for the cosine of the double angle, which is 2 cosine squared of t minus 1. Remember, x is cosine of t, so y being 2 cosine squared of t is just going to be 2 times x squared minus 1. So this would imply that y is equal to 2. Again, instead of cosine being squared, I'm going to write it as x being squared minus 1. And this type of problem is where I put on my additional little note here that's critical to understand. X and y are restricted because they're results of cosine functions. The cosine only outputs values, or the range of the cosine, if you want to be official, is only values between -1 and 1, including -1 and 1. Same thing with the cosine of any angle, honestly. Your values are only going to range from -1 to 1. So while you may think your Cartesian form is y equals 2x squared minus 1, And it is, don't get me wrong, it's 2x squared minus 1, given that the x values are always bounded between -1 and 1, and the y values are always bounded between -1 and 1. So here's how I would graph this initially. I'd graph y equals 2x squared minus 1, which is this curve right here. It's just a parabola shifted down 1 unit, right? And it also has a lead coefficient of 2. You can double check my values there, but it is true that those values are correct. So when x is 0, y is -1. And when x is 1, you get 2 minus 1 or 1. So this is 1 comma 1. And this point over here is -1 comma 1. All right, so that would be actually the graph of y equals 2x squared minus 1. However, that's not what we're graphing. We're graphing a set of parametric equations, specifically a set of parametric equations where the x values cannot go beyond 1 and the y values cannot go beyond 1. So I have to erase those little edges there. Let me go ahead and include these points. All right. So this is actually the graph of the parametric curve. Now, the piece that's going to be really interesting is the path of travel. Let's go ahead and start with just x equals 0, just to see what this looks like. So when t equals 0 is what I meant to say. When t is equal to 0, that will imply that x is equal to 1 and y is equal to 1. So at time 0, we have this point, I'll call it t sub 0. That's our initial time value. And then when you plug in a different time value, and here I'm going to plug in maybe time equals pi over 4, because it's a trig function, you want to plug in values you can actually use here. So time equals pi over 4. I notice that the x value is now cosine of pi over 4, which is 1 over root 2. And the y value is cosine of 2 times pi over 4, or cosine of pi over 2, which is 0. And notice that that is actually right, let me plot this here, right here. So this is time pi over 4. So I note that the path of travel is like this. And you think, great, the path of travel must be like this here. And it is true. It actually is. That's the path of travel. Until you get to that edge over there. And let's just see what this edge over here is. I know what the time value is going to be, so I'm just going to plug it in to showcase it. When time is pi, our x value, cosine of pi, is -1. And our y value, cosine of 2 pi, is +1. That was supposed to be a -1 right there. Sorry about that. So this point over here is time pi. This point right here, time pi. But then what happens? Does it just jump over here and continue? Nope, because the two functions we have are continuous functions. So there's no hopping around magically here. There's no teleportation allowed on this curve. So instead, let's go ahead and find out what happens as time goes beyond pi. Let's try time equals 5 pi over 4. Why not? So time equals 5 pi over 4. Remember, the x value is the cosine of time, and that'd be the cosine of 5 pi over 4, which is a -1 over root 2. The y value is the cosine of twice t, and that'll be the cosine of 5 pi over 2, which is 0. So at time 5 pi over 4, which is beyond time pi, we are suddenly right here. This is time 5 pi over 4. So essentially what happens is we circuit back around and go this way. So the path of travel is rebounding. And this is very, very common with parametric curves. You get this rebounding behavior. Visually, it looks like this. Let me go ahead and press play on this. And you can see that the path of travel started at time 0, and then at time pi it pops off this, comes down, climbs back up, and it'll do this forever and ever and ever. Let me speed this up a little bit so you can see. But that is the particle doing this path of travel on this parametric curve, which is x equals cosine of t, y equals cosine of 2t. Notice that it is not the same as y equals 2x squared minus 1. It looks like it is, but actually y equals 2x squared minus 1 has a range from -1 to infinity, whereas this function that we're actually dealing with has a restricted range. So the punchline is just always remain aware of the domain and range restrictions of the parametric equations before eliminating the parameter. At best, the parametric curve will be identical to the Cartesian curve, but more often the parametric curve will be a restricted version, and that's what we've just seen. The final example in this video is just more of a physics style example talking about particles in a plane, that type of thing. So the position of an object moving in circular motion is modeled by the given set of parametric equations. Describe the path of the object by drawing a directed graph. So a directed graph is basically what we've been drawing, a graph of these parametric equations with directions on it. So here we have this, we're asked to graph this. And again, my advice still holds. If you have trig functions here and you can't easily eliminate the parameter, you might want to look for trig identities. And in this case, we have one very special trig identity, which is that the sine squared of an angle, specifically 2t, plus the cosine squared of the same angle should equal 1. That is, if we take x and square it, and we take y and square it, it should be 1. And that will be our equation that we graph. A very, very nice equation here. Let me go ahead and just draw in a set of axes. So you should note, by the way, as I'm doing this, that this one is not like any of the previous examples. All the previous examples, we were given equations that we could eliminate a parameter on, or in the last example, instead of eliminating parameter, we could write x or y in terms of x because x was cosine, and we let y, since y was cosine of 2t, we used a trig identity to write y in terms of cosines and then did that. But this is a very special type of curve where you have to use a combination of these two functions to create a new equation, essentially. So it'd be very challenging to write sine of 2t in terms of the cosine of 2t or vice versa. So it's much easier just to say, listen, I know that sine squared of an angle plus cosine squared of an angle is 1, and so we can just say x squared plus y squared is 1. That happens every once in a while. Just look for it. It's kind of an important identity to keep in mind. So there's our unit circle. It's a unit circle because it's x squared plus y squared is equal to 1. And so we have the graph. We're done, with the exception that we need to know the path of travel. So that just takes a little bit of, tiny little bit of work, right? Little t equals 0, and then maybe a t equals pi over 2. That's all I really need. In fact, in this case, you'll see I might want to do a pi over 4. So time equals 0, we get the following. X is 0, and y is 1. Time equals pi over 2, we get that x is equal to sine of twice pi over 2, which is sine of pi, which is 0. And y is equal to cosine of twice pi over 2, or cosine of pi, which is -1. Well, that didn't really give us a great path of travel because it just started here. Whoops, that's not where it started. It started here at x equals 0, y equals 1. That was time 0. And then at time pi over 2, we landed here. It didn't really give us a good path of travel. I don't know. Did it go to the right or to the left? So you go ahead and just do one more in between time 0 and time pi over 2. Do time pi over 4. At time pi over 4, the sine of twice pi over 4 is the sine of pi over 2, and that would be 1. And the cosine of twice pi over 4 is the cosine of pi over 2, which would be 0. So x equals 1, y equals 0. That would be time pi over 4, which is right here. And so we can see the path of travel is this way. It's the reverse direction, or clockwise actually is really nice way of saying it. It's a clockwise path of travel, and it will just constantly repeat this path of travel, by the way. So that's how you do graph parametric curves using elimination of the parameter. Again, eliminating the parameter is a blanket statement. If you can solve for t, you'd like to do that. But often with trig functions, that's just not going to be the case. And so you need to start using trig identities to help you out there.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.